All right, so let's talk a little bit about the next kind of problem, which is determining the end behavior of a polynomial function. The end behavior of a polynomial function is exactly what the name implies, is what's happening to the graph of the function at its ends. Let me show you some examples. So here's what I'm about to do. I'm going to take a polynomial function. Let's just say y equals a times x, and let's raise that to the b power. I'm going to put some sliders on both of those. Okay? So, obviously we see a straight line here. The reason why we see a straight line is because the exponent, I'd like you to focus on b right now. b is 1, so that makes sense why we would get a line. Do you see what's going to happen if I decide to make b a 2? Yeah, that's a quadratic, right? Because now we have x squared. Look what happens when I change that to a 3. There's the graph for a cubic degree, or a third degree function. Here comes 4. Noticing anything yet? Here comes 5. So what are you noticing? A pattern here, right? There's a nice little pattern. For example, pattern that we can come up with is if we type in even numbers, 2, 4, 6, 8. Look at the ends. Okay? The end behavior at the ends of this graph looks like both of those arrows are going up and up. Do you go back and look at the a value? See how a is a positive 1? Do you see what would happen if I decided to make a, I don't know, a negative 1? See what happened to that graph? It flipped over. Okay? So, a couple of conclusions we can make about the end behavior of even degree functions. What do I mean by even degree functions? Go back to 1. Remember, I'm talking about that exponent there being an even number, like a 2, a 4, a 6, or an 8. What they're trying to show you right over here is this little column right there. If the degree is even, you would get a graph that would go up and up. If a is a positive, that leading coefficient right there is a positive number, so you might want to draw that in. Up and up. Okay? If a is negative, you'll get a graph that goes down and down. Okay? So back here, take a look at what happens when I put in odd numbers, like a 1. See how one arrow right down here goes down, the other goes up. 3. One goes down, the other goes up. I'm going to be reading these from left to right. The left arrow's down, the right arrow's up. 5. Left is still down, right still up. 7. Again, right? 9. 11. See what's going on? Left arrow's down, right goes up. Okay, that's because a is positive. It kind of looks like and behaves just like a straight line, right? If I go from 11 here to 1, it's almost like by the power of math, I'm kind of just straighten this line out there, and just goes just like that, right? That's a technical term, just like that. Okay? So, when the degree is odd, an odd number, a 1, 3, 5, 7, down, up, down, up, down, up, down, up. Okay? So, back over here to that picture. Let's do some more drawing. Okay? So now if I'm over here and looking at these two guys, if A is positive, a down-up graph would look something like this. Okay? Do you see what would happen without me going back to that graph, what a negative A would do? You're right. Just like it flips over that parabolic shape, it's going to flip over that up-down, that down-up graph and make it go up-down. Kind of like this. Okay? So what you can do, a cool thing that you can do, is if the polynomial is already in standard form, you can go ahead and cut all that extra stuff that's out of it and just look at two things. And that is the leading coefficient and the degree. Okay? Since the degree is odd, we have now narrowed it down to either down-up or up-down. Because the 4 is positive, that means it must be this graph right here and not this one. So all you need to do when you answer that question is down up. Okay? See how this one is even? So that means we're either here or there, up, up, or down, down. And because that leading coefficient, see how none of that matters. That's the cool thing, is none of that rest of that matters. That leading coefficient's negative, so that means we got to be down and down. Can't be that one. So you see how they did that. So looking at this one, Nothing else matters, like that Metallica song. And then we're looking at this right here. Odd and negative right there. So if I had to describe this graph, the degree is odd, which I still have highlighted here in green. And then what was A again? That leading coefficient is negative. So we are going to have a graph that is up and down. Okay? Let me erase this right here. We can describe this graph as up and then down. All right, here's the visual proof. See how I typed it into the function right here? Negative 4x to the third plus 2x plus 7. Tough to see here. How about I zoom out a little bit? Oh, would you look at that? See how it's from left to right, it starts up and then it goes down. So it's an up-down graph. All right, if you flip that note sheet over, let's take a look at the back and let's see what we can do with some of these problems here. And from what you guys were looking at before when I was showing you all those different graphs, realize with the odd degree functions, notice that graph would tend to turn a little bit. You know, some graphs, depending on the way the polynomial is written, and when you graph them, we get something called turning points. Okay, turning points is just a big fancy word for when the graph changes direction from increasing to decreasing. Okay, so if we look at both of these two functions down here, look at A right there, 1/2 x cubed. I typed that into the graphing calculator or get a table of values, take a look at that graph. It's going to ask you, I'm going to ask you a couple questions. I want you to describe the graph, including the end behavior, turning points, increasing, decreasing intervals. I'm going to limit that. Just worry about telling me this. Okay? Don't forget about, just forget about that. Tell me the end behavior and then the turning points. Okay? So do you notice what's going on here? The end behavior on this one would be down and up because that first arrow is going down. Second arrow is going up. You always read from left to right. Do you notice what it says right here? It's kind of interesting. This kind of bothers students a little bit at first. See how it says there's no turning points? The reason why there's no turning points is if I trace this from left to right, is there any point where I stop increasing and then turn to decrease? Do you notice there's never a point in time where that actually happens? So since I never go from increasing to decreasing, there are no turning points. However, when you look at the second one, look at B. We graph that one. The end behavior would be up, then down, and then notice right here there are two turning points. Okay, two turning points. So all we would have you do here, and all I want you to do when you're answering these questions on the homework, is go ahead and use some tech and graph that out and tell me the turning points. So just using the tech on this, did you see what we just did? I just typed it into a graphing calculator. Negative 3x to the third plus 2x squared minus x minus 2. Hit graph. Take a look at that end behavior right here. So describe the end behavior. We describe that graph as the end behavior as being a up, down. It's supposed to be a slash. Looks great, doesn't it? And then let's talk about turning points. How many turning points does this thing have? You got it. See how at this point it's only decreasing. It never turns around and starts increasing. So there are 0 turning points to that graph. Okay, so hopefully it helps with that kind of problem there. Definitely want you using the tech that you have available to you in class or at home with Desmos to answer that question. So if it says graph it, don't graph it. All I want you to do is just talk about the end behavior and then talk about turning points. Okay, so let's move on to the next part of the lesson with another video.